welcome to Quantum Photonics. And here we are with a very interesting topic and a very interesting person. So, Dr. De Rham has a recent book which she will also be talking about here, and she has been playing with gravity in her entire life. She is a diver and, as such, experimenting with her body's buoyancy in the Indian Ocean, and as a pilot, soaring over Canadian waterfalls on dark mornings before beginning her daily scientific research. As an astronaut candidate dreaming of the experience of flying free from Earth's pull, and as a physicist discovering new sides to gravity, irresistible personality by exploring the limits of Einstein's general theory of relativity. The Beauty of Falling. In this book, De Rham shares captivating stories about her quest to gain intimacy with gravity, to understand both its feeling and fundamental nature. Her life's pursuit led her from a twist of fate that snatched away her dream of becoming an astronaut to an exhilarating breakthrough at the very frontiers of gravitational physics. While many of us presume to know gravity quite well, the brightest scientists in history have yet to fully answer the simple question, what exactly is gravity? So, she will be speaking about that when she makes her presentation. And I would like to tell you more about our guest speaker. Professor Claudia de Rham is a professor of theoretical physics at Imperial College London and is a member of the American Academy of Arts and Sciences. She researches gravity, particle physics, and cosmology in pursuit of a more fundamental description of the nature of our universe and the laws that govern it. Her work has provided new perspectives to understand the origin of the universe, its accelerated expansion, and the fundamental nature of gravity. She is ranked among the most impactful researchers in fundamental physics of the past decade, and her contributions to science has been recognized by numerous grants and awards, including the Royal Society Wolfson Merit Award, the Adams Prize for Contribution to Mathematics, named as the Simmons Investigator in Physics in 2020, winner of the Blavatnik Award for Young Physicists in the UK in 2020, and of the Bitnaruska Senior Guest Professorship Award in 2022. She is the author of a popular science book, The Beauty of Falling, A Life in Pursuit of Gravity, and is a co-author of a volume of the Encyclopedia of Cosmology with A.J. Tolley. I am very excited and very proud to introduce our special guest speaker today, Professor Claudia de Rham. Claudia, welcome to Quantum Photonics.
Thank you. Thanks a lot. Thanks a lot, Cecile, for the very, very nice introduction. Very nice welcome. Hello, everybody. So yeah, it's really a pleasure to be here. And as Cecile mentioned, I do like to think of gravity, how we experience gravity in a physical sense, as well as thinking more fundamentally about this phenomenon. And so while I go through what gravity is and what I mean by the beauty of falling, I thought maybe I could share some slides. I don't know if Cecile, if you have access to the slide that Cecile has been sharing.
Yes, the slides are at the top of the screen.
Okay. So if you can look at the slides, and then if I start with this first slide, that's actually, you'll see the cover of the book, The Beauty of Falling, A Life in Pursuit of Gravity, that really mixes a little bit of the scientific appeal towards gravity. It's a scientific journey into understanding what gravity is, which is far from finished, and really trying to encourage people in taking part in that journey. But also the more personal aspect in playing and challenging gravity in a way or another, in an intellectual way, but also in a more physical way, which I think is kind of a witty character in and of itself. So if you go into slides 2, I like that picture because it you may have the impression of me being a theoretical physicist, being overcoming gravity in everything I do, but in my everyday life, this is more, it looks much more like my own experience with gravity, and really just um, being there, subject to gravity like everybody else, of course. And I think we all have this idea of trying to challenge gravity. It's one of these phenomenon. As a young child, as the first phenomenon, there's the first physical law that we really try to challenge, that we appreciate, and we try to challenge and play with it in a continuous way. And actually, on that picture, what's interesting there is that if you think about Olivia, that character falling, I don't think she found the fall particularly beautiful, but that's part of the book in embracing the fall so that you can find it beautiful, to find it the serenity that there is actually in the beauty of falling, in the beauty of free fall. Once you know how to embrace it and appreciate it. And what's interesting in that picture is that she's clearly under stress. And it's not because of the fall itself. It's very much about the anticipation of what is to come next. After the fall, once the fall has broken and you hit the ground, I think that's really what we worried about. And it's a sort of an excuse there in saying that actually what we feel, or what the negative aspect we may be relating to gravity or to falling, is not related to gravity at all. It is related to the anticipation we relate to what will happen upon impact. But what we feel upon impact after a fall is nothing to do with gravity. What we feel upon impact when we fall down, when we hit the ground or the water, or whatever it is related to more electromagnetic forces between in the atomic bonds between the cells in the body and that of the ground or the chair or whatever. And it's very much related to something quite fundamental, but nothing to do with gravity. Is related to Pauli's exclusion principle, which prevents two particles, like for instance two electrons, from occupying the same state at the same time. And I know this is quantum photonics clubhouse, so I know you must be very used to this phenomenon, quantum effects, and this inability actually at the core, the fundamental level, to share space at the same time, to share the same state at the same time. That's really what we feel upon impact. And the reason I'm going through that is to say that this actually has nothing to do with gravity. Actually, if you really want to experience gravity, you have to forgive what will happen next. You have to sort of make abstraction of this anticipation and just think more freely. And I'm not telling you to jump or anything like that, but that's really what the scientists will say in how you try to experiment with gravity. And then there is something really beautiful into it. And so if you go to the next slide in the picture number 3, this is whoever you want it to be, more enjoying, embracing this feeling, or as close as possible, of a feeling of free fall, and actually enjoying gravity, enjoying the moment, enjoying that experience. So this is someone experiencing falling. There is a beauty in this falling, even though falling may be associated to failing. Ultimately, at this level, falling is really beautiful, and so is failing. And I would say failing is also something quite intrinsic in us as human beings, in the scientific endeavor, in the scientific enterprise, and also in gravity itself. And I will discuss about some of the pitfalls, some of the failure of gravity. And that is actually something very serene in itself, very beautiful, because it allows us to make progress. It allows us to enjoy things for where they are right now, and then understand where to go, where to move forward when we understand where things are not working the way they should be, and therefore make discoveries. So where we're going for discoveries is going to be very much what I want to be talking about towards the end of this little talk. But for now, let's just enjoy gravity. Let's just try to imagine we can appreciate this falling of almost free fall. Although in that picture, as you can see, whether it's the lady in orange or that is really me in blue. This is me going skydiving in a virtual skydiving experience. You see that I don't have a parachute there. It's almost free fall, and it's very serene. It's very, very happy memory, very beautiful feeling. but it's not quite, because in both situations you still have the friction of the air, and that pushes very much against part of your body. And that's even more so true on the picture on the top right, which is a virtual skydiving. Actually, you compensate the effect of gravity with that off the pressure of the air that acts on your body. And so you do feel very much this pressure of the air, and it acts on every cells of your body. It tones them apart a little bit. You feel that. You feel very much the pressure of the air. And the pressure of the air, this is a force, is actually compensating the force of gravity that push you down. And yet you don't feel very much that, or at all, this force of gravity. Not because it's not there. Actually, I would say gravity can be described as a force. That's absolutely fine, but simply because the way it acts on all of the cells in our body is in the same way. So gravity doesn't push or tear your cells apart. It acts on them in the same way, in such a way that you can't distinguish that feeling. So we don't have in our body, we don't have any cell, we don't have any taste bud, we don't have any eardrums, we don't have anything that will allow us to feel, to taste, to hear, to smell that feeling of gravity per se, even though it's still there. And to provoke you even a little bit more, you can imagine, if you go to slide number 4, if that helps, otherwise you can just imagine closing your eyes. You can imagine you're in outer space, you're orbiting the Earth. So something Cecil mentioned is that I did really want for many years, for 20 years of my life, trying to become an astronaut. I was an astronaut candidate, and I tried to do many different things to become an astronaut. And in the end, it didn't work out. You have to read the book as to why and how and everything I tried to do. But still, I can imagine, I think we can all imagine, and I think we all have deep down this desire of being in outer space. So a lot of us has this desire to be in outer space, being an astronaut. And in that case, you are actually falling so freely. Can you imagine what that means, to fall so freely, in the sense that you don't have any effect from any other force around you? You just have gravity, and you experiencing gravity so freely that you don't feel anything at all. It's complete freedom, with no feeling whatsoever. And that's because gravity, even though it clearly acts on you as you're orbiting the Earth, you are falling. Your trajectory is that orbit, and you are attracted by the Earth, is simply how this trajectory looks like. We'll talk a little bit more about this in a second. You are falling, you are experiencing gravity, but you don't feel anything at all, because gravity is acting on every single particle in every single one of your cells, in every single one of what makes you, and even in the air, in your spacesuit, in exactly the same way. And that is something, to my mind, very beautiful, very universal, very profound about gravity. This is something we call the equivalence principle, that tells us that gravity acts on everything and everyone throughout the universe in really very much the same way, in the same way. It's equivalent, it's very democratic, it is universal in every sense of the word. And then that also means that not only it acts on us as human beings, or it acts on an apple, like we think of Newton having an apple falling on top of his head, and that's how he understood some of the aspects of gravity. But that's not only that, it acts on planets, and it acts on stars, and it acts on interstellar dust, and on everything and everyone in exactly the same way. And actually, Galileo and Newton were the first to understand really how universal gravity is. And Galileo envisioned this experiment from the Leaning Tower in Pisa already centuries ago, thinking of dropping a feather and a hammer from the Leaning Tower of Pisa. It's not clear whether the experiment really took place, but it's very much at least a mental picture, in thinking that you can drop those two objects and they would hit the ground. You drop them at the same time, and they would hit the ground at the same time. Probably that didn't happen, or even if it did, we all know, because of the friction from the air, that they wouldn't hit the ground at the same time, because not because gravity is different, but because the friction of the air would then affect the feather and the hammer in different ways. But nowadays, we can test the equivalence principle extremely well. It's been tested on the moon, for instance, where there's no friction. That's been tested during the Apollo mission. That's not why the Apollo mission was sent, but that they did. That was one of the first tests they did on the moon. But we have here, for instance, at Imperial College London, some experiments, and throughout the planets there's various experiments. Also in space there are other experiments that test this equivalence principle and really tells us that this universality in which gravity acts on everything and everyone is very, very precise. And we can measure absence of deviations in 1 part to the 15. So if you can take two, for instance, molecules, or two, let's say two atoms with slightly different properties, or charges, or nuclei numbers, or even ultimate spin in the end of the day, and you can see that they experience gravity in exactly the same way in 1 part to the 10 to the 15. So that's a million billion precision on how they experience gravity in the same way. And there's a famous microscope experiment in space, actually, which measures that extremely well. And this is, I'm sure you all heard about it to some extent, but I'm going on about it because to me it's really very much what attracts me to gravity, to how profound it is in that we can never escape it. Whatever we are, whoever we are, however insignificant we may be, we still, with respect to the eyes of gravity, are completely equivalent. And to me, that's something very profound in how we all actually connect because of that through gravity. And we all at the same footing through gravity. Now, because of this equivalence principle, because of this universality of gravity, when that's what really pushed scientists at the beginning of the last century, or the end of the one before, to understand that there must be something much more profound about gravity than being a trivial force between two objects. If gravity acts on everything and everyone in the same way, then it can't just be about two masses attracting each other. If it acts on everything and everyone in the same way, the information about it has to be encoded in something which is more fundamental than just the masses themselves, just the objects themselves. It has to be encoded in some underlying structure of space-time, underlying structure of reality, which is much more profound than that. And if you go to the next slide, just to give you a picture, we now understand, thanks to Einstein's theory of general relativity, so Einstein's theory of gravity, which was established in 1915, that one way to understand gravity is that, for instance, masses like planets and stars, but also you and me and anything present in the universe, we curve the structure of space-time around ourselves because of our mass, but not only because of our mass, just because of our presence. So anything that carries just energy, like light, doesn't carry any mass, but it carries energy, that will also affect the structure of space-time around itself. And anyone else is experiencing, is living on that space-time, is living on that fabric of space-time, and so is experiencing this curvature, and therefore is experiencing this gravitational attraction. And so that tells us that anything and everyone is affecting space-time, and we are affected by space-time. So everything and everyone is affecting everything and everyone. We all connected. We all connected. Hi. Okay, perfect. Okay. Hi. Yeah, I don't know what happened. Sorry about that.
Maybe it's not your fault. Maybe it's a glitch in Clubhouse that's
I
happening
see.
once in a while. But everyone, while you were away, was saying how excited and how very honored we are to have you. And we hope
Thank you.
that you did not have this bad experience because it's a rare
No,
occasion.
no worries. No worries. So
So,
I don't know where I was when I got kicked out. But maybe I was saying how precisely we understand gravity, and that we understand the position of the moon within a millimeter precision. I don't know if you heard that.
Yeah, yeah, I think. How about you guys, Bob and Frank? Did you hear
Yes,
that?
that's as far as
Okay.
I remember.
Okay, perfect. So, actually, for some respects, we understand gravity, and we understand gravity even more precisely than any of the other fundamental forces that we know of, and even what we can see with our own eyes, which is light, which is electromagnetism. Um, so I'll talk a little bit about electromagnetism because it's useful to draw a comparison between electromagnetism and gravity. And if you go to slide number 9, I'm sure, I mean, this is a quantum photonics chat, so I'm sure you, you're familiar with electromagnetism. You can think of electric and magnetic forces as two different forces, or two different phenomena, but actually they are different manifestations of the very same phenomenon, which is electromagnetism. And sometimes that manifests itself as the electric force, that is a repulsing force between two uh, same charges, for instance, two negative or two positive charges, or a positive attraction, an attraction between two opposite charges. And then sometimes we can think of the magnetic force, which has helped us navigate and through thousands of years. But really, different depending on your perspective, and if you are someone moving with respect to someone else, then what you identify as an electric and what you identify as a magnetic counterpart is relative. Depends on your perspective, and that's okay. That's absolutely fine. So it's not two separate phenomena; it's actually one phenomenon, which is electromagnetism, and they are very much related to one another. Now we know that electromagnetism as a force is related to light. Light is actually an electromagnetic wave. And we know, for instance, that when there's a big storm, when there's a thunderstorm, and there's a quick discharge of electricity in the air, what happens is that electric charges are being accelerated, and that produces lightning. That produces an electromagnetic wave, which is light, and we're all used to that. We know that when you accelerate electric charges, for instance, when you accelerate electrons, you produce electromagnetic waves, you produce light. Electromagnetic waves are just a fancy word for saying light. And for me, light would be electromagnetic waves of any possible frequency, any possible color and frequency. I know some people reserve the terminology light to be electromagnetic waves just within the visible, but I'm just going to be quite agnostic about it. And we use that in our everyday life, as I'm sure you know even better than I. We use this phenomenon of accelerating, for instance, electrons and producing light through this phenomenon, bulbs. And we use that in antennas, which accelerate again electric charges to produce radio waves for telecommunication. And radio waves are just electromagnetic waves, which is just light. And we can understand that electromagnetism, this force of electromagnetism, deep down is actually carried by a secret messenger, which is light. Electromagnetic waves are what carry the electromagnetic force. And so if you have two electrons located some distance apart, it is deep down this electromagnetic waves, this deep down light, which communicates to the two electrons the fact that they have to be repulsing each other. And there is very much of a communication, propagation of information going on there. Now, I'm really interested in gravity, and I know, and you probably hear a lot of the time that gravity is not a force and it's not shouldn't be compared to electromagnetism because gravity is the manifestation of the curvature of space-time, and that's what I was saying before. And that's true. That is absolutely true. That gravity is the curvature, as manifested by the curvature of space-time. But deep down, gravity is still a force. Fundamentally, gravity is still a force. You just need to dive a little bit deeper in the structure of gravity to appreciate the force of gravity. And we have actually detected the force of gravity through gravitational waves. And that phenomenon is very, very related, very similar to electromagnetism. And actually, just like a, if you go to the next slide, maybe in the slide 11, just like we know that we can produce electromagnetic waves or light when we accelerate electric charges, the same is true for gravity, and we can produce gravitational waves, or what I call glite, by analogy to light in my book. That's just me calling it like that, but I think it makes sense. We can produce glite by accelerating charges with respect to gravity. And what are charges with respect to gravity? Well, you can think of masses. Masses are charges with respect to gravity. They're not necessarily charge electric charges, but they are charged with respect to gravity. Anything actually is charged with respect to gravity. So, if you wanted, if you were looking at the motion of photons and light itself, it would produce gravitational waves as well. Anything produces gravitational waves if it's not too symmetric. And so, us in our heart, for instance, when our heart beats, it changes the distribution of masses a little bit, and that produces gravitational waves. Um, we produce gravitational waves when we move around all the time. We produce gravitational waves, but no offense to you or me or anyone here, the gravitational waves that we produce are very, very small amplitude, small magnitude, because gravity is actually an extremely, extremely weak force. And we know that gravity is a very, very weak force as compared to the other forces of nature, because, for instance, if I rub a balloon on my head, a party balloon on my head, and I pull it apart and I move it away, then it will attract my hair. What happens in that process is that as I rub the balloon in my hair, I transfer some of the electrons, and when I pull the balloon away, then because there's been an electron transfer, then they become one is becoming electrically charged and the other one is becoming electrically negatively charged, and they attract each other. But there's just a transfer of a few electrons, and this transfer of just a few electrons is sufficient through this electromagnetic force to compensate the whole gravitational pull of the whole mass of the Earth. And so I'm saying that just to give you an insight on how ridiculously weak gravity is. The whole effect of the whole mass of the Earth is compensated by just a few electrons being pulled away. So that's just illustrating how weak gravity is as compared to electromagnetism. So now, to produce gravitational waves with sufficiently high magnitude so that they can be observed and have really an impact on us, you see that it can't just be you and me or little electrons running around. It has to be very astronomical masses being accelerated with respect to one another. So you have to think of stars or black holes being accelerated with respect to one another so closely with such high masses that you can think of stars or black hole about to merge on one another. And then they will produce very high intensity gravitational waves. And these have been observed. If you go to the slide number 12, the next one, then we know that, for instance, when black holes or when neutron stars or when stars are orbiting each other and just when they're sufficiently close to merge on one another, then they produce gravitational waves which are quite high magnitude. And then these gravitational waves, once they've been produced, they propagate through space and time, just like light propagates through space and time, relatively unaffected by anything and anyone they encounter, all the way up to the time when they reach our instruments here on Earth. And for this first signal, this first event that took millions of years to reach us here on Earth, through our instruments. And on the bottom, you've probably seen a picture of that in the past already, is a cartoon picture of the interferometers that are used to detect gravitational waves. As the gravitational waves pass through our instrument, they distort space every source slightly, and through lasers that are sent in vacuum chambers, vacuum cavities, kilometers long vacuum cavities, they measure the space between the two mirrors as gravitational waves pass through, and they see that space is being distorted. And on the right, you will see, I'm sure you will recognize the first gravitational wave, the signal from the first gravitational wave event detected here on Earth. That was detected in 2015 and then announced in 2016. So gravitational waves really do exist, and they're the direct analog to electromagnetic waves. They're direct analog to light, and gravitational waves, light, is actually the secret messenger for gravity. Is how fundamentally the gravitational force is being communicated between two masses, for instance, or between any two objects in the universe. Now, just like for, if you go to the next slide, you'll see that just like for light, we know that light can be thought as an electromagnetic wave, but we also know that at the quantum level, light can be described by a fundamental particle, which we call the photon. And there's a particle wave duality in quantum mechanics. That means that if you take light of a particular color, of a particular frequency, and you reduce the intensity as much as you can, you will see that it's being carried by finite discrete quanta of energy, which we call the photon. And so light of a particular frequency can come with one amount of energy, or twice that amount of energy, or three times, or billions of times that, but then nothing in between. And to make sense of the laws in physics in the way we think of them, it has to be the case that the same is true for gravity. So we have detected gravitational waves, we have detected the wave nature of gravity, but really fundamentally, gravity must be also carried by a fundamental particle, which we call the graviton. And if we were to think about the gravitational waves that we have observed, and were, in principle, reducing the intensity as much as we could, there should come a point where the energy carried by those gravitational waves, when you think of just one frequency, then it is quantized, it comes in discrete quanta of energy, which we call the graviton. Now, for the gravitational waves that we have observed, they are made out of 10 to the 44 gravitons. So that's a huge amount. That's, if you want to think about it, for me, it's quite spectacular, because together, those gravitational waves, they add together 10 to the 44 gravitons working together in harmony. And together, they manage to squeeze or push the space between two mirrors here on Earth, located 4 kilometers apart, by a distance of less than a proton. That's 10 to the 44 gravitons working together in, I would say, the biggest team bonding exercise in the whole history of the universe that you can imagine. And that's quite spectacular in itself. So detecting a single graviton out of the lot through interferometers wouldn't even be challenging experimentally. That would go beyond Heisenberg uncertainty in principle. And so to prove the quantum nature of gravity and to prove the existence of gravitons, one would need to engineer different type of experiments, which are not directly through the detection of gravitational waves, but say through interferometers. As before, it's not impossible necessarily, but it will be challenging. And in some cases, it's even theoretically impossible by Heisenberg uncertainty principle. Now, if you go to the next slide, the slide number 14, I discussed about electricity, the electric force, and the magnetic force, and the gravitational force. Actually, so far as we know, we think that there are 4 fundamental forces that we know of, and there may be more, but we haven't discovered them yet. And this is electromagnetism, that's one of them. The weak force, which is responsible for the structure within the atoms. There's a strong force, which is responsible for the confinements of the quarks within the protons and neutrons in the nuclei of the atoms. And then there's the gravitational force. And we can put them all roughly in the same footing, and we think that they should all be part of a much bigger unifying theory, a grand theory of everything that we don't know what it is yet, but we think that that should be possible. What at very least, what we know for sure is possible is to unify some of the other forces. With gravity, we know that this is going to be extremely challenging, but we know that we can unify the weak force and the electromagnetic force together into an electroweak theory. And the weak force, which is a weak force, I'll talk about it in a bit. But in some sense, it's also just a different manifestation of a very similar, the same phenomenon, which is part of the electroweak theory. That's a unification of some of the fundamental forces of nature. And so for the weak force, we also know that we can represent this fundamental force at a fundamental level with particles. And those particles, in this case, they don't have very appealing names, but they are called the W and the Z bosons. Now, the weak force is very important for life, is very important for life on Earth. The weak force is responsible, as I said, for the atomic structure and is responsible for fusion in the sun. That's through a phenomenon related to the weak force. And we use related things to the weak force, for instance, for medical imaging. So we do have applications of the weak force. But it's not something that most of the time we are not here communicating through the weak force. We're mainly communicating right now through the web, through the electromagnetic phenomenon. We're not communicating through the weak force because the weak force is weak. And if you go to the next slide, in slide number 15, nowadays we understand that the Higgs mechanism, the Higgs boson, and the Higgs mechanism are actually responsible for the weakness of the weak force. We understand that the weak force, we're experiencing it as being a weak force because it only operates on subatomic structures, and beyond that, it switches off. And it switches off because of the Higgs mechanism. The Higgs mechanism is responsible for giving a mass to the fundamental particles, which are the W and the Z boson. In giving them a mass, it makes it harder to excite them, and therefore it makes it harder to experience this weak force, which is mediated by the W and the Z boson. Actually, to understand how the Higgs mechanism and the Higgs boson are responsible for weakening the weak force, it is useful to think of empty space. It is useful to think of what we think of a complete vacuum. And you can imagine you have a vacuum chamber where you remove anything you can imagine in that. So you have the best vacuum chamber in the planet. You have the best vacuum chamber in the universe. Let's put this vacuum chamber even in the middle of a cosmic void with nothing in it, absolutely nothing. You have removed every possible thing out of it. And let's imagine you have shielded it from every light and cosmic ray and anything else that could come from the depth of the universe. And then if you go to the next slide, number 16, you will see that this vacuum is never really completely empty of energy. We know that even in the best vacuum, there's a constant bubbling in and out of quantum fluctuations of all of the particles that we know of, including that of the Higgs. And it is this sea, this vacuum sea, or what I will call the sea bath, that fills the whole structure of space and time throughout the universe, which is responsible for giving a mass to the W and the Z boson. Actually, if you go to slide number 17, you can see that this is a newspaper announcement. I haven't made that. That's actually in the news. The discovery of the Higgs is the proof that empty space is actually quite something. We discover what nothingness is made out of is quite something. Even empty space, even we consider the absence total of any particle, is still made out of a Higgs bath that has an effect on other particles. Do you understand how this sea of vacuum fluctuations have an effect on other particles, particularly that of the Higgs bath? You can go to the next slide, the slide number 18. I don't know how much you can see on your screen, but on slide number 18, you can think of this Higgs bath as really your bathtub or the ocean. It's really a sea of quantum fluctuations, a sea of the Higgs bath. And light or massless particles, like the photons, they won't interact very much with this bath, with this medium. And so they're not very much affected by it, and they're free to propagate at wish. However, more massive particles, like the W and the Z boson, interact much more strongly with the Higgs bath. And so this Higgs bath should also have an effect on those massive particles. It inhibits their dynamics to some extent. And that's how the Higgs mechanism, this Higgs bath, affects the W and the Z bosons, affects the dynamics, and makes the weak force being weak, because those more massive particles are responsible for the propagation of the weak force, for mediating this weak force. So now one thing that we know, if we go back to gravity and what we started with, and which is to me quite precious about gravity, is the fact that it's endowed in the equivalence principle, meaning that everything and everyone is acting on gravity, and gravity is affected and is affecting everyone. So if this Higgs bath is not just a figment of our imagination, if it is something real that actually has an effect on other particles, and that's how we understand the masses of the W and the Z bosons, is not just concepts, it's actually reality, then it should also have an effect on gravity. And so now we can start trying to understand what it would mean for the Higgs bath to have an effect on gravity. And if you go to the next slide, the slide number 19, we understand, as I mentioned before, thanks to Einstein's theory of general relativity, how different things, different objects in the universe, through their presence, they curve the structure of space-time, and it is through this curvature that we experience gravity. But now, at the time when Einstein's theory of general relativity was derived, we didn't know yet about this Higgs bath and the quantum sea of fluctuations of all the particles that we know of. But now we do. And so now we can actually try to understand what it would mean to include this Higgs bath, which fills all of space and time together, everywhere, all the time, into gravity. What is the effect of this Higgs bath on gravity? And it's not something which is just local at one point in space, or one point in space and time. It's actually something everywhere, absolutely everywhere in the universe. You have this Higgs bath. It fills every pocket of emptiness in the universe. So it is there in this room, it is there wherever you are, right here. You're breathing it to some extent, if you want to. If you want to think of it as being material, it's not material, but it is there. This energy of the vacuum should be there everywhere, constantly, uniformly in the universe. Here and in empty space, and in a black hole, and even in the middle of a cosmic void, it should be there. And that, therefore, is not something local that curves space-time locally. It's actually something that pushes the universe everywhere all the time. It is something that leads to an expansion of the universe. It's a cosmic expansion, but not only an expansion, an accelerated expansion. It leads to the expansion of the universe going faster and faster, which is what we observe. Actually, if you go to the next slide, if that helps, if you look at different objects throughout the universe and you look at them, we know from observations that everything seems to be moving away from us. And the further away we look, and the fastest they seem to be moving away from us. And that doesn't tell us that there's something specific about us and where we are in the universe. It actually tells us that this has to be happening according to anyone in the universe. And so what must be happening is that the space between any two things in the universe must be stretching. And this is what we observe. We're observing the stretching between us and these stars and these objects. And the further away an object is, there's more space to be stretched. So the faster the object will seem to be moving away from us. The object itself doesn't know it's moving, just like we don't know we're moving. It is space in between that is being stretched and pulled apart. But one thing that we know, which is not depicted in this picture, is this is going faster and faster. Not only is the universe expanding, but this expansion is accelerated. And this makes complete sense with the knowledge that the universe is also filled with this Higgs path, is filled with this quantum sea of fluctuation that carries energy and that should lead to an accelerated expansion of the universe. But the bad news is that the expected accelerated expansion of the universe from the Higgs path is way too fast. And it's not way too fast, but just a factor of 2, a small error that I can just ignore. If you go to the next slide, you'll see that it's actually wrong by at least 28 orders of magnitude. This is what 28 orders of magnitude is. This is the biggest discrepancy in the whole history of physics. On the one hand, if you go on to the next slide, we have general relativity, which is the best description of gravity that we know of and which has been tested within 15 orders of magnitude in some aspects, and is impeccable agreement with everything that we know of for gravity. And then on the other hand, we have particle physics, an understanding of the Higgs mechanism, an understanding of the whole standard model of particle physics, the whole constituents of matters, and all of the other three fundamental forces of nature. We understand that extremely well. It's all self-consistent, and yet we put those two things together and we are led to the biggest discrepancy in the whole history of science. And it's not that it's the wrong thing. It does lead to an accelerated expansion of the universe as we observe. This is right. It's just the rate of this expansion is way too fast. And so most of the time, you have heard of this idea of dark energy that says, oh, we need all of this substance out there in the universe to explain why universe expansion is accelerating. This is a little bit misleading because it's not surprising that the universe is accelerating, and we don't really need anything new beyond what we already know should exist, namely all of the Higgs path, all of the quantum vacuum fluctuations of particle physics that we know of and that should be present. And their vacuum fluctuations is being the fluctuations at the very least, the quantum fluctuations of the particle is being probed in different ways, not on gravity, but otherwise in different ways. So it is a bit misleading to say we need some new type of unknown dark energy out there, because we already have what it takes to make the expansion of the universe accelerating. Actually, the controversy is not knowing what dark energy could be. We have a very, very solid candidate for it. The controversy is why that doesn't lead to a much bigger effect as compared to what we observe. And we would have expected this vacuum energy to lead to a much faster, accelerated expansion of the whole universe. And so, in fact, this, as I mentioned, is the biggest discrepancy in the whole history of physics. And it is one of the biggest challenges we have in theoretical physics at the moment. We don't understand why this vacuum energy doesn't have an effect on gravity much higher than what we would have expected it to have. And in fact, there's very few possibilities that have been proposed. One of them is just an entropic principle, which says, well, if it had been any different, we wouldn't be there to ask ourselves the question, and therefore, well, let's not dwell on that. And that, to me, is not a very satisfactory response. And so, for lack of a better possibility, what I'm going to propose here, and this is something which is just a proposition, is not proven, I can't tell you whether it's right or wrong, it's just a suggestion of one way to think about it. And the way to think, I like to think about it for a second, just as an entertainment if we want to, is to wonder whether it's possible that this discrepancy is only there because we are thinking of how this vacuum energy acts on gravity in the same way as we think of gravity in the standard laws of physics through general relativity. But it is possible that when we're thinking of the effect of the vacuum energy and the fact that it really fills the universe on such big scales in space and time, and so uniformly in space and time, then actually its effect on gravity should be different as compared to what general relativity would have predicted. And it is just a possibility, but for that, I'll need to understand what I mean more precisely by that. And so to understand that, you need to go to the next slide. And then you just imagine on the top, on the very top, what you can see is two distant galaxies. Let's imagine that there are two objects located on the other side of the observable. What I mean by observable is the Hubble radius of the universe today, which is 10,000 million trillion kilometers long. So imagine two galaxies being located on the other side of the universe away from one another. Now, according to Einstein's theory of general relativity, the graviton is massless, is a massless particle, like the photon, and so it has an infinite reach. And so, in principle, those two objects located on the other side of the universe from one another will still technically exert a gravitational attraction on each other. So that's one thing that's very much diluted with the distance. But what's even more important in that picture is that to understand the dynamics and to understand the dynamics of the universe, you also need to account for all of the energy contained in the Higgs bath in between, for the vacuum energy in between. And this integrated over those huge distances is what leads to a huge, huge, huge impact. Locally, the amount of vacuum energy on Earth, in this room, in the solar system is utterly negligible. But if you integrate something which is utterly negligible over the largest possible volumes in the universe, then you end up with something which is actually very, very significant. And this is what's happening. This is what is happening in Einstein's theory of general relativity. You need to account everything throughout the universe, and particularly all of this vacuum energy, to explain the dynamics of the whole universe. And that's really a lot. And the possibility I'd like to raise is that maybe this is too much to ask. Maybe there is a point where gravity switches off, just like we've seen that happens for the weak force. Maybe gravity switches off and it's only operational on some distance scales. So those distance scales should still be very large, because we know that on scales of clusters of galaxy scales, gravity should still be there, affecting things, operating things in the same way as we think it should do in Einstein's theory of general relativity. But when we go to much, much, much larger distances, maybe gravity switches off. And if it did switch off in a similar way as the weak force does on super beyond the atomic scale, then you wouldn't need to account for all of this vacuum energy in between. You will need to account for a smaller amount of vacuum energy in between. And so the effect of this vacuum energy on the evolution of the universe, on the accelerated of the expansion of the universe, will still be there, but you take less into account, and so it leads to a smaller accelerated expansion of the universe. And this gets diluted over time, and so over a time period of the age of the universe now, the effect of this vacuum energy would be much smaller as compared to what you would have expected in Einstein's theory of general relativity. I am running very much out of time, so let me just send an email quickly to my next appointment, so I can be there in a bit. I'll just take a second. Sorry to do that.
Bob?
Okay. Okay. So so I have time, if you have time, to finish. Okay, so in principle, what we need to do, in practice, what this means is that we need to think of how to do the same thing for gravity as what nature has done for the weak force. We know gravity is a weak force, but we want it to be weak in the same sense as well as the weak force, in that it switches off on large distances. And so, since nature has already told us what to do for the weak force, what it means in practice is that the W and the Z bosons that carry a force are massive particles. So in here, what it would mean is that the graviton, which carries the gravitational force, has to acquire a mass. So we need to think of a theory where gravity is massive. Gravity is not massless, as is the case in Einstein's theory of general relativity. It is massive, not in the sense that it's big, but in the sense that the fundamental particle that carries the gravitational force is a massive particle and not a massless particle. Both in Einstein's theory of general relativity and in massive gravity, there is a fundamental particle there, which is the graviton. The only difference between the two is that in Einstein's theory of general relativity, the graviton is massless, whereas in massive gravity, the graviton is massive. And this possibility that gravity could have a finite range, or in practice that the graviton could be a massive particle, has actually been explored throughout the past centuries. It's actually quite a natural possibility. If you go to the next slide, on slide number 24, you see, I'm sorry, it's not very diverse in terms of gender, but you see at least gentlemen here from different places on the planet throughout the centuries. And all of them, in one way or another, and many others that I haven't pictured there, but all of them, in one way or another, have thought about what it would mean either for the force of gravity to have a finite range, in the Newtonian sense of gravity, when it was people thought more of a Newtonian gravitational force, from Newton to Laplace, and then when people understood that there was an Einstein theory of general relativity and that fundamentally was carried by a particle, which we call the graviton, and embed this much more on a quantum field theory framework, and then people throughout the past century have been exploring the possibility that the particle that carries the gravitational force, the graviton, could be a massive particle. And that was explored by Pauli, it was explored by Salam, and many different people throughout the past century. It's not that way because we drove. Sorry about that. So yes, they have explored that throughout the centuries, and at the time they explored that just because that's an interesting scientific question in and of itself, not because they knew that the universe expansion was accelerating, and they wanted to reconcile it with the amount of vacuum energy that we would expect, but they just thought of it because it is a natural questions to ask ourselves, and we should ask ourselves those natural questions and explore. And if we have understand what it would mean, then we can compare it with Einstein's theory of general relativity and understand what is happening. But this possibility was always completely refuted throughout the centuries, and not because observations weren't matching out, but simply because it was impossible to make it work theoretically, purely on theoretical grounds. And if you go to the next slide, the slide number 25, these are quotes that are pulled out from various papers in the past century, scientific papers from these different people trying to work out how, if and how, one can think of a theory of massive gravity, a theory where the graviton would be massive or gravity would have a finite range. And I don't know how much you can see on the slides from your phone or from your screen, but you'll see that it doesn't appear very positive, very positively. Throughout the centuries, actually, every time people try to understand what it would mean to have a theory of massive gravity, they were always faced with what we call no-go theorems. They are theorems, mathematically proven theorems that tell you it's impossible. There would be a fundamental inconsistency that would make it impossible. And the reason for that is that people were finding what we call ghost. And that's written on that slide. One of the quote that I pulled out from a scientific paper is written plagued by ghost. That's really a scientific paper, and it is a scientific literature. And a ghost is not it can be something of science fiction, but in this context is actually what we call a particle which has a negative energy. And if you if you think that there could be particles of negative energies, then those particles of negative energies, they would allow to annihilate any particle with positive energy that we are made out of, any fundamental constituent of matter that we are made out of instantaneously. And so if ghosts were present, it would mean that the whole structure of reality would look completely different. Everything would have just been annihilated instantaneously. So clearly that's not the case. And so clearly you can't have a theory with a ghost. And at the time, throughout the century, the conclusion that people came up with is simply to say that this would mean that the theory of massive gravity is impossible. And in fact, if you want to have a theory of massive gravity, you can go to the next slide. If you want to, what it would mean is to have a theory where it's possible to get rid or to trap this ghost. And this is this picture of the Ghostbuster. And this is what we actually made it possible through our theory of massive gravity. If you go to the next slide, slide number 27, with Gregory Gabaradze and Andrew Tolley. So these are two of my collaborators. And the way we engineered a way to get rid of this ghost was much more of a trap. And actually, this trap, if you go to the next slide, that's just a cartoon picture of how you can represent it in your head. This trap for the ghost, you can think of it as a confined space, a constrained space, like an infinite loop. These are like Asian stairs or Penrose stairs, where the ghost is trapped to be in a sort of topological space from which it cannot evade, from which it cannot interact with anything else, and therefore it can't do any harm from that. I mean, in reality, this is just a symbolic way to picture it. There's a lot of math that goes beyond it. There's a lot of things that go beyond it. But this is sort of the way we engineered to make it work and to have a theory of massive gravity. Now, it wasn't as simple as that, even though we had a completely bulletproof mathematical proof that showed that the ghost did not appear. It took years and years and years to convince the rest of the scientific community that our math did work out, and that the theory of massive gravity that we had developed was indeed free of the ghost that people thought had to be always present. And that's because people, even in science, come with all sorts of different scientific cultures, different languages or different perspectives, different argumentations. And so when you do science, you always had to adapt yourself to those different perspectives. We have throughout the years to adapt our logic and our way of thinking to those people that come up from different ways, and make sure that we translated our logic in a way that made sense to them. Throughout the years, we had to do that to the point where there was finally no unanswered questions. And it was kind of overwhelming throughout the years to do this. Time after time, we went through many different processes, but in itself, that was never the goal. Proving the theory of massive gravity could exist was never the goal, really. What it was the start of the journey, a start of a journey where we could finally have a theory of gravity where we can contemplate what it would mean for gravity to have a finite range, for the graviton to be massive, and most importantly, to compare it with Einstein's theory of general relativity, to have an alternative out there so that when we do observations, we know what it would mean to have an alternative. We know what to compare it with. And so what I'll end up with, I'm running very much out of time, I'm sorry about that, but what I want to end up with is just give you a glimpse of an idea of what it would mean to compare it and to understand what it would mean more observationally, more concretely, for gravity to be massive, for the graviton to be massive, and for gravitational waves to be massive. And you can't just measure the mass of the graviton in the same way as you measure, or you experimentally measure the mass of fundamental particles like the W and the Z boson, because, as I mentioned, well, probably it's extremely challenging to detect a graviton. We certainly haven't done it yet, and it will be very hard to do it even in the future. Very challenging. So by itself, it's going to be very hard to just detect one graviton and identify its characteristics. But what we can do, if you go to the slide number 29, is use very precise tests of gravity to measure aspects of gravity, and in particular, understand whether or not gravity is massive, and if put an upper bound on the graviton mass if possible. So what you can see on this picture number 29 is an artistic view of the LISA space interferometer. It's a space mission that has been approved. It has the go-ahead now. It will be launched in the 2030s. It will be a space mission that will be following the Earth in orbit and measuring gravitational waves, detecting gravitational waves with very, very low frequency, because the arm width of this interferometer will be much, much longer than what it is we can do on the planet. So it will allow us to detect gravitational waves of very, very, very small frequency. And the idea is not engineered specifically to test massive gravity, but it is there to test gravity to some level. So if you go to the next slide, the one number 30, on the top, if a particular event is the type of signal you may expect if the graviton has no mass. And at the bottom is the type of signal you may receive if the graviton has a large mass. And you see that the signal appears more compressed as compared to if it has no mass. And that's because if the graviton has a mass, then different modes, different frequency for gravitational waves would be traveling at a slightly different speed. And in particular, very, very low frequency would travel ever so slightly slower than the speed of light, ever so slightly slower than the higher frequency. And so the gravitational waves which are emitted later, they travel slower, and the ones which are emitted later, they travel faster. They sort of catch up a little bit, just a tiny little bit, with respect to the lower frequency one, the first ones, and so the signal appears more compressed. This is very pronounced. You don't expect quite something as dramatic, but it is the type of signal you may be looked at, not quite so pronounced, but a little bit like that. And so by comparing for a specific event, the type of signal you would expect with what you actually observe, you can put an upper bound on the graviton mass. If the graviton has no mass at all, then it won't be compressed at all. And the larger the mass, the more compressed it is. And so from that, you can put an upper bound on the graviton mass. We have already observed gravitational waves, so of course we can already put an upper bound on the gravitational mass, the mass of the graviton. But the upper bound we have at the moment is still at least 10 orders of magnitude above what we would find useful for cosmological purposes. So we really need to go to much more precise instruments to being able to see that, possibly in the future. And let me just end up maybe by the last slide, number 32. You can look at 31, it's just for fun. But let me end with the last slide, number 32, in saying that, as I mentioned before, the goal is never to prove us right or wrong or anything like that. It's very much an exploration in science. It's very much an exploration of even what is possible in nature. But I do find it fascinating in this field in how detecting gravitational waves now and in the future may allow us to understand something quite fundamental about the infinitely small, about the nature of the graviton, the smallest possible thing that you can imagine, about how infinitely small quantum fluctuations in the vacuum can end up having an effect on the largest possible distance scales. And that will allow us as well to understand if and how we connect gravitational with objects on the other side of the universe from us, some 10,000 million trillion kilometers away from us. And so there's a very beautiful connection between observing gravitational waves and allowing us to make a connection between the infinitely small and the infinitely large effects in our universe. The infinitely insignificant ending up being the most significant elements in our universe. So again, I'm sorry, I'm running so much out of time, but I'll stop here.
Yeah, thank you so much, Claudia. Such a very detailed and great presentation. So, I would just like to ask you at this point, how much more time do you have for us? Because, yeah, I think some members of the audience would also like to ask you some questions.
So if 10 minutes or so, is that okay?
Yeah, that's okay. So, as of now, maybe I will pass about asking a question. Well, if I have the chance later, I will do so. So, but I
Yeah,
wanted to
10,
ask
10,
you.
15 minutes. Yeah, that's okay. Yeah.
Yeah, okay. So we have Frank here, and earlier I think Hermes was making a study about gravitons. When you were out of the room, we were having a casual discussion. So,
Uh-huh.
but
Uh-huh.
yeah, but I'll give the mic to Hermes later also, and there are comments here on the room chat. But I want to ask you first, maybe just two questions for now. Why are you passionate about gravity? And also, the second question is the title of your book, The Beauty of Falling, is quite intriguing. But this seems to be paradoxical. What do you mean by that? So I think I'll ask you those two questions. Thank you.
Okay, yeah. Okay, let me maybe start with the second one, the beauty of falling. Yeah, as I mentioned at the start, when we think of falling, most of us, me included, we don't necessarily think of it as being beautiful in any way. We may think of the pain. We may think of falling as something related to failure as well. Um, and it is paradoxical, but also it is in embracing this anticipation of what may happen that I think a lot of positive things can come in, and there's different ways in which I think falling is beautiful. I think falling is beautiful in the sense that as you think of gravity, and I can tell you in a bit as well how much why I think that gravity is so beautiful, but also there is an aspect in falling that if you learn how to embrace it, and if you learn um, to allow yourself to to go into the fall itself, then you realize that it's one of the most serene experience you can imagine. And so what I wanted to do is demystifying a little bit gravity and the fear of falling. Um, there's this idea that falling and failing is ubiquitous in everything that we do, and it is ingrained in the scientific process. It is part of progress. It is part of the process as well. So once again, rather than facing failure as an embarrassment, we should really celebrate it. And of course, the main message of the book is about mine, because we're talking about the book, but it's about my own failure and how it ended up being making me who I am, something I wouldn't want to go back onto. But also about Einstein's theory of general relativity, which is facing its own failure. It is facing its own failure in the sense that, as I mentioned it, but also it is facing its own failure in the sense that we know that when we're trying to quantize gravity at very high curvature level, then something is breaking down, and we need to have a better theory to describe what is happening there. And that failure is actually the best feature I think a theory can have. In and of itself, it should be seen as something quite positive that allows us to know where to look for new discoveries and how to move forward. So there is a beauty in this failing of gravity. There's a beauty in the failure of everyday's life, in how we have little failures, and in the scientific discovery, this is how we make progress. And there is a beauty in gravity itself. Now, this is also related to why I am so excited about gravity, because for me, and also in writing the book, I was very much driven by sharing the passion I have for studying gravity. It is something which is so universal. It is something that connects us all together. So it is, I say it in the book as well, it is the ultimate way of communication in some sense. because everything will be connected to gravity. There's no better way. Of course, it's very, very weak. these are uh, these are technical challenges you have to overcome, but fundamentally, it is something so profound and putting us all on the same footing. And so this universality aspect of it, which is present everywhere all the time throughout the universe, to me, this is something too fundamental not to care about.
Thank you so much, Claudia. Yes, so I just wanted to share that I had been trying to watch the gravitational waves very closely until they declared that, hey, LIGO declared that we have this gravitational wave. They
Yeah,
found, yeah, and that was this is a very exciting age of gravitational wave
it
astronomy.
is. It
Yeah.
is. It is amazing. Yeah, yeah. And to me, it's really amazing how. I mean, it is the opening of a new era because it allows us um, to see now the universe in a different way. It is a different way to get some insight on the universe, which we wouldn't have had before. It's like we have a new color, but it's even more powerful than that. Yeah.
Yeah, yeah, thank you. So I'd like to give the opportunity to Frank or Kevin and also for Bob to read also and ask if he has questions, some comments here on the room chat because our special guest may not have much time. So Frank and Kevin, just flash your mic if you want to speak. Go ahead, Frank.
Yeah, thanks, Cecile. Hope you can hear me okay.
Yeah.
Yeah, yeah, Claudia, yeah, welcome to you to Clubhouse and
Thank you.
Quantum Photonics Club. And while there was the glitch, I was saying to my fellow moderators, thanks, Cecile and Bob's great efforts to be able to invite you here. And it's really a treat and such a illuminating, beautiful slides and a great lecture to be able to hear you in
Mhm.
person and ask you a question
Thank
as a
you.
I'm a fan of physics, but I'm a practicing engineer. So you see, there's a gap. But I do have a few questions after listening you in popular science channels, and I actually my heart is pumping because I think this is actually a historic, maybe witnessing history of science with
Uh-huh.
very
Uh-huh.
high probability. I think it's I think kudo to you and for your conviction and contributions and your fellow um, uh, collaborators.
Thank you.
Yeah,
Thank you.
yeah. So since you're limited by time, quickly I have just two questions. Let me put them out and together. So first is my just curiosity as a amateur that when you say speak of the ghost, is it a are you referring to the mass being something like a charge also have a negative mass thing? That's one question one. And the second question related to you mentioned the the experimental aspects of verification of your theory prediction. Lisa, for example, the
Yeah.
space info thermometer, but I didn't catch the detailed figure you give. Is it in is it you think Lisa will be able to, or is still some way mileage to go? If it's a negative, then do you think can you mention a few others for possible candidates in terms of manual means? Like we have invited a guest here speaking about a PDA, it's a pulsar timing array.
Yeah. Yeah.
Would those
Yeah.
be
Yeah.
can contribute in or potential
Yeah.
candidates? Yeah,
Yeah.
that's my question.
Absolutely. Okay. So very good. Yeah. So let me answer the first question first about the ghost particle. That particle would have a mass, but actually a positive mass. It's not the mass the problem. The mass of that particle will be the same as that of the graviton. That is not the issue. It is very much it's kinetic energy. So for you and me and for normal particles, it costs us energy to move, and then we get more tired, and we when we eat we convert some of the energy we have into kinematic energy as we move around. So it costs us energy to move around. For a ghost particle, it costs it negative energy. So actually, as they move around, they are freeing energy. So they don't need energy. They release energy so they feel very happy to move around, and the faster, the more energy they release. And so it is a particle, if it did exist, would completely stop making sense of any reality that we're experiencing. It goes exactly the opposite way of anything we know of. But it's not only that it's something surprising, is that as soon as this would be present, then it would also, because of all energy that it releases, us as the positive energy that we are made out of, they would absorb that energy and they would get very excited. And so the whole universe as we know it would completely decay away. So it's not about the mass per se. It's about all the way the dynamics of this particle works out. It's a particle with negative kinetic energy, and it's a difference between having a negative mass and a negative kinetic energy, because if it's related to its mass, then you can, so long as you don't excite the particle too much, so long as you're working below the mass scale, then you don't need to worry too much about it. But for the kinetic, the particle can just decide to move around, and then it has some negative energy. So you don't have a control, you don't have a lever to play with in that case. And that's why it's fundamentally a complete destruction as soon as you have a ghost-like particle. Okay, so this is for the ghost. The second question, very good. For the detection of for LISA, for instance, and future gravitational wave observations. So LISA will be sent in the 30s or so, we're hoping. By itself, we're hoping that it could put a constraint on the graviton mass to be, I forgot the exact number, but roughly 10 to the minus 26, maybe 20, maybe around maybe 26, 27 electron volt. What we want is really graviton mass to be for the order 10 to the minus 32, 33 electron volt. So it's still a little bit higher as compared to what we would want, but it's getting closer to the interesting range, particularly if you can go to very precise measurements with that. Now, with LISA, and then ideally with pulsar timing array, and with other things like the Simon Observatory, we are also hoping, we as us, not me, I'm not part of these experiments, but we're also hoping to be able, ideally, to observe primordial gravitational waves, which are not emitted by the merger of two black holes, for instance, but which were emitted by quantum fluctuations at the very beginning of the universe, and those quantum fluctuations in gravity at the very beginning of the universe were then stretched through the process of cosmic inflation to a point that they are now imprinted and propagate as primordial gravitational. So either you observe those primordial gravitational waves with PTA and with LISA possibly, or you see the imprint on the CMB through B-mode polarizations in the CMB with the Simon Observatory. But being able to observe primordial gravitational waves would allow us to constrain gravitational waves with a much lower frequency even, and that will allow us, for instance, with PTA, it could go very close to the constraint. And if we do really observe primordial gravitational waves, we could put a constraint on the graviton mass to be of the order of 10 to the minus 29 electron volt, or almost close to what we expect it to be. So we're really very much entering the realm where we can start seeing whether or not the graviton has a mass of the order of magnitude that we would want it to be.
Thank you very much. Yeah.
Yeah, thank
Kevin? Or...
Frank, you were about to speak. I'd like to give the chance to Kevin to ask a question. Kevin, uh,
Oh yeah, hi. Yeah, I'm getting kind of a red bar, but hopefully you can hear me. And I know the time is short, so. But yeah, like Frank says, my mind's spinning for this one, especially with no time. So I'll just, uh, no pun intended. But yeah, I'll just say that what do you think that maybe the differences of emergent gravity and loop quantum gravity L cube G, the differences there,
Yeah.
you know, maybe of those
Uh,
two.
so they're quite different in the original assumption they use, the framework they use, the language they use. Um, but the reality is, I think at the moment, there are many different candidates out there. It can be string theory, it can be loop quantum gravity, they can be causal sets, they can be emergent gravity. All of each single one of those ones, plus others, they all start with a different, even language, a different way of what thinking of what is fundamental, whether some of them have space time built into them, some of them don't even have a notion of space time built into them. I think the reality is, it's at this stage, it's even hard to know whether we're in the right track, or we need to think of things even more differently. Some of what I work on at the moment is trying to understand how to make connection between things we can observe in our everyday life, and we can observe maybe with gravitational waves, through actual observations, um, with ultimate embedding or high energy completion of gravity, or what gravity is at the fundamental level, without being too specific on the model, because every single one of those models are quite different, but also it's hard to make connection for them with specific observables. For most of them, we're not at this stage yet. I mean, for all of them, I would say we're not even at the stage where they can come up with a list of signatures, and we look at the sky and we say, okay, we observe this and not that, and therefore it is this completion and not that one. And so I think we have to open up a bit our minds and how we think about it.
Oh, okay, yeah, yeah. I think my mic was unmiked the whole time. Hopefully you didn't hear anything as well. And I'm not gonna say a bug, but
No,
okay.
it's absolutely fine. Absolutely fine. Um, yeah, I'm sorry. I'm gonna need to go now. Sorry to taking all your time.
uh, we are very thankful that you came here. So we hope that we can invite you again because I know that you have so much to talk. And I just want to ask you: is this book already out on the? Is it out in the market already? Can people buy the
Yeah,
book?
yeah. You can have it out, and I think Maria probably sent you a link and then a code where you can have something like 30% off or something like that. So I don't know the details, but the code she
It
sent you, you can.
It's here on the room chat, but I think just ask me, any one of you who would like to get the book, because I can send you the link. You can ask me on my Twitter account.
Yeah,
So,
yeah.
yeah, because I could
Uh,
not make this public also. So,
yeah,
anyway,
absolutely. Yeah. And then
um,
otherwise, it should be on Amazon or wherever you are on the planet. It should be available. But I know that Blackwell ships worldwide.
uh, all right. So, yeah, I hope that we can invite you again, Claudia, at some other
Okay, thank
time.
you.
Thank
Thank
you.
you.
So,
Thanks a lot. Thanks.
o-
Bye-bye.
Thank you.
okay.
Bye. Bye.
Let's Bob, can we count down to close the room?
Absolutely. And because in interest of time, we're going to go with five. Kevin, you're going to be five.
5.
Five.
4.
Frank, I'm three. So three for me. And Cecile, you're two.
2.
And
Yeah.
Dr. Claudia, you're number 1.
Oh,
One.
number one.
Thank you, everyone. Bye.
Thank you.
Thank
Thank
you.
you
Bye
so much.
bye.
Yeah. See you.
Bye.
Bye.
Hope
Cheers.
you will
Thanks a
come
lot.
back.
Thank you. Bye bye.